Hello students, today we are going to study next point, demultiplexer tree. Similar to multiplexer, we can construct the demultiplexer having more number of lines using demultiplexer having less number of lines. This is called as a demultiplexer tree. It is also called as a cascading of demultiplexer, and this concept will be clear by solving the problems, that is the demultiplexer tree. Then first is obtain 1:4 line demux using 1:2 demux. This is the first problem, that is the demultiplexer tree. That more number of lines using demultiplexer, less number of lines, that is called as a demultiplexer tree. Obtain 1:4 demux using 1:2. 1:4 demux, one input line, 4 data input lines, 4 output lines, 2 select lines are required. But 1:2 demultiplexer, 1 select line, 2 output line, 1 data input line. So we require the 4 output line. So 1:2 demux, we use the 2. There are the 1:2 demultiplexer are required. So first is 1:2 demultiplexer. 1:2 demultiplexer, 1 D in, 2 output lines Y0 Y1, 1 select line S0, and another one is 1:2 demultiplexer is required. And for that 1:2 demultiplexer, that is one select line is required. That 2 select lines for 2 demultiplexer we cascade. This is the demux 1 and this is the demux 2. There are the 2 demultiplexers are we cascading, and here 2 select lines are for the 2 demultiplexer we cascade. And for second demultiplexer output Y2 Y3, these are the outputs. That is the 1:4 require 4 output line, so we cascade the 1:2 demultiplexer. Next, there are the one enable input for both multiplexer. From that enable input we connect one NOT gate, and from that we get the another one, the select line, that is S1, and this is the S0. And these enable is used for the cascading purpose. Here we use the NOT gate because at only one demultiplexer will be enabled at a time. So here a NOT gate is used in between 2 enables. There are the and this is for second demultiplexer is D in is required, and this first D in and second D in we cascade and we get one D in input. These are the select inputs. 2 select lines are required, 1 data line, 4 outputs, that is the 1:4 demux. There are the 4 output lines, 1 D input and 2 select lines. So we cascade the 1:2 demultiplexer. This is the 1:4 demultiplexer obtained from 1:2. So there is a truth table, select inputs. There are the 2 select inputs S1 and S0, and outputs Y3, Y2, Y1, Y0, LSB to MSB. These are the outputs. When S1 and S0 are 0 0, Y0 output is selected, Y0 output is selected, and this D in data is routed or distributes the Y0 output. So here is the D in, and otherwise all outputs are 0. When S3 and S1 and S0 are 0 1, 0 means 1. So Y1 output is selected. So output D in, this D in data is distributes for Y1. So output D in is 1. Otherwise are 0. When 1 0 means data 2. So Y2 output is selected. Select line select the data 1 0 means 2. So Y2 output we here select, and D in data distributes for Y2. So here is the D in, and otherwise are 0. When 1 1, select lines are 1 1, D in data, this D in data input, this is distributes to Y3 because S0 and S1 are 1 1. So here is D in is and otherwise 0. This is the demultiplexer. We obtain multiplexer tree, demultiplexer tree, that is obtain 1:4 line demux using 1:2 demux. Next one example, obtain 1:8. Next example, obtain 1:8 using 1:4 demux. Then 1:4 require, 1:4 require, we obtain 1:8. So this is the D in and this is the 1:4 demux 2. This is the 1:4 demux 1. For demux 1, outputs y0, y1, y2, y3, y4, y5, y6, y7. These are the outputs, and from this 1:4 require, there are the two select lines on first demux, second demux we parallelly here connected, and these are the common for S0, S1, S1, S0, and from this we get the two select lines as a S0, S1, and for here D in data we connected common as D in and the one output as a D in. And for 1:8 required 3 select lines, but 1:4 are the 2. So enable of first demux, second enable of demux enable, we cascade and we connect one NOT gate in between them, and we get the another select line. There are the 3 select lines are from the for the 1:8. That is the 1:2 require 1 data input line, 8 data output lines, 8 output lines, 3 select lines. We obtain from the 1:4 demux. This is the obtaining 1:8. Then select inputs. Select inputs are 3 truth table, S2, S1, S0, and outputs from Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. 0, 0, 0. 0, 0. Select lines are 0, 0, 0. D in data distributes to Y0. So Y0 output is selected. Otherwise are the 0. 0, 0, 0, 1. This D in data distributes to Y1 because select line data is 0, 0, 1 means 1. So here is the data. Next, up to this 7, that D in data distributes to Y0 to Y7. So this is the 0, this is the 0, here is the D in 0, 0, 0. Next data 0, 1, 1, this is the 3. So Y3 output is selected, this D in data distributes to Y3, 0, 0, 0, D in, 0, 0, 0, 0. Next is 1, 0, 0, that is data is Y4. This is a 4, so D in data distributes to Y4, 0, 0, 0, 0, D in 0, 0, 0. Next 1, 0, 1 means 5. Select line data is 5, so Y5 output is selecting, so D in distributes to Y5, 0, 0, 0, 0, 0, 0, D in 0, 0. Next 1, 1, 0, that is a 6, so D in data distributes to Y6 output, so 0, 0, 0, 0, 0, 0, D in 0. 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, D. This is the demultiplexer. We obtain 1:8 demux using 1:4. Next is the one question is asked. This is very important. That comparison between Mux and Dmux. Comparison between Mux and Dmux. Multiplexer and demultiplexer. Multiplexer is the types of combinational logic circuit. Demultiplexer is the combinational logic circuit. In a multiplexer, number of data inputs are n. In a demultiplexer, there is a data input line is 1. In a multiplexer, number of select lines are required m. In a demultiplexer, number of select lines are required m. Number of data output lines for multiplexer is 1, and in a demultiplexer n. Relation between input and output lines are and select line n is equal to 2 raised to m. In a demultiplexer also n is equal to 2 raised to m. Operation many input, one output in a multiplexer, that is multiplexer is a data selector. One input, many output, that is a data selector. This is the difference between a multiplexer and demultiplexer. Multiplexer applications are used in a time division multiplexer at the sending end, and the demultiplexer is used in a receiving end. And for the demultiplexer, that IC 1:4 demultiplexer IC 74155 use, and that IC we study in a practical detail, that is the 1:4 demultiplexer required 74155. And that demultiplexer, very important point, that is comparison between Mux and Dmx. Then next point, use Dmx in a combinational logic circuit. Combinational logic design. In a combinational logic design, this is the demultiplexer that used in how is in a last lecture in multiplexer also we study the combinational logic, that SOP expression, POS expression or truth table is given, that implement in a demultiplexer. That combinational logic circuit, first is here we take one problem, implement full adder using demultiplexer. Full adder truth table A, B, C in, and outputs sum and carry. Outputs, and these are the inputs. This is the truth table of full adder. Then 0 0 0 sum is 0, carry 0. 0 0 0 1 sum 1, carry 0. 0 1 0 sum 1, carry 0. 0 1 1 sum 0, carry 1. This is the truth table of full adder, and from that full adder which demultiplexer required, and that full adder we implement in a demultiplexer. 1 0 0 1 sum 0, carry 1. 1 1 0 sum 0, carry 1. 1 1 1 sum 1, carry 1. Sum 1, carry 1. Then we have to write the expression for the sum, that is a summation m. For the sum is equal to summation m from truth table. That sum is where 1, that input we have to consider. Here is sum 1. So this is 0 0 1 means data 1. 1, here is sum is 1. 0 1 0 means 2. Next 1 0 0, that sum is here 1, that is a 4, and here is 1. So sum equation, should be get that outputs y1, y2, y4, y7. Next for the carry is where 1, that inputs are selected. Here is carry 1, that is a 3. Here is 1, that is a 5. Here is carry 1, 1 1 0 means 5. Next 6 and 7. That is the outputs y3, y5, y6 should be ORed to the carry output, and these are this is the sum, and from that sum and carry from this truth table, where is the sum is 1, that input is considered, that expressions are 1 2 4 7 3 5 6 7, and from that we have to implement the demultiplexer. Which demultiplexer is required? There A, B, C in, and the possibilities are 8. So 1:8 demultiplexer is required. From that truth table you have to decide which demultiplexer is required. We require here in that, for that full adder, 1:8 Dmux. 1:8 Dmux, how many data input lines? 1 D in, this D in connected to logic 1 always, and 3 select lines are required. 3 select lines are required, S0, S1 and S2, and these A, B, C in full adders inputs are the select lines of 1:8 Dmux. So this is A, B, C in, and outputs are Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7 and Y8. And that these are the outputs for up to Y7, and from these outputs we connected as a half adder, sum and carry equations, that we implement full adder using demultiplexer. So from the sum and carry equation, that is the sum is where is sum is 1 for 1 2 4 and 7, that line 1 2 4 and 7, these are ORed together. These are the ORed together these are the ORed together, these lines, and this is the sum. And where is the carry one? Carry for the 1, 3, 5, 6 and 7. Oh, 3, 5, 6 and 7. These are we ORed. Sorry, here is a OR gate. We connect the OR gate, and this is the carry equation. This we designing full adder in a Dmux. That Dmux is required 1:8. From that Y0 to Y7 lines, sum required. Sum is for 1, 2, 4, 7, and carry is for 3, 5, 6, 7s are connected here for OR gate, and S0, S1, S2, these 3 select lines of the are the inputs of the full adder A, B, C in, and data D in is required as connected to logic 0. So this demultiplexer 1:8 is implemented, that is full adder is implemented in a Dmux 1:8. Next, this is the chapter completed for SYIT, and SY computer half chapter is your completed, third chapter. Next lecture we study next point. Thank you.